In order to start with the procedure to determine the position of a rigid body, we recall the concept of rigid body. When we presented the models used to describe the bodies in mechanics, we defined rigid body as an idealized model where the points of the body cannot change their position with respect to each other. The position of a body is always determined with respect to a frame of reference, for example the laboratory where we perform experiments with the body, and we describe its position in a coordinate system attached to the frame of reference. The position of a rigid body is completely determined in the three-dimensional space by specifying the positions of three arbitrary points A, B, and C of the body provided they are not collinear, that is, these points are not lying on the same straight line. For if we fix only the point A of the body, then the points B and C can be rotated over the spheres of radii given by the distances of the points B and C from the point A, and with the center at the point A. If the point B of the body is also fixed, then the point C can still be rotated about the axis passing through the points A and B. If we fix the 3 points A, B, and C of the body, then we fix the position of the whole body, that is, we completely specified its position in the space. Since we use 3 non-collinear points and the position of a point is described by 3 coordinates in a coordinate system, we need 3 times 3, that is 9 data to determine the position of a rigid body in the coordinate system attached to the frame of reference. If we use a Cartesian coordinate system, then these data consist of the Cartesian coordinates x, y, and z of the points A, B and C. By definition, the distance between any 2 points of a rigid body is always the same even if the body moves. We can apply the Pythagorean theorem to describe the distance between the points A and B, and we can write that the square of the difference between xa and xb, plus the square of the difference between ya and yb, plus the square of the difference between za and zb is equal to the square of the distance d between the points A and B. We have 2 other equations for the point pairs A and C, and the point pairs B and C as well. The distances between the point pairs on the right-hand side of the equations are constants, whereas the coordinates of the points are functions of time for a moving body. By virtue of these 3 relations between the Cartesian coordinates, from the 9 data describing the position of a rigid body only 6 are independent. Therefore, the instantaneous position of a rigid body performing an arbitrary motion is determined by 6 independent data. In other words, a freely moving rigid body has 6 degrees of freedom as opposed to a freely moving point mass which has only 3 degrees of freedom. We can choose the 3 coordinates of an arbitrary point of the body and 3 angles describing its orientation to specify the 6 independent data for a rigid body, where the angles are the so-called Euler angles. In order to describe the position of a rigid body in the coordinate system with the coordinates x, y, z and the origin O, we attach another Cartesian coordinate system with the coordinates x', y', z' and the origin O' to the body. As a result, if the position and the orientation of this coordinate system is known, then the position of the body is specified. Its position is given by the coordinates x null, y null and z null of the point O' in the coordinate system x, y and z. We need other 3 data to determine the relative orientation of the 2 coordinate systems. In this respect, the positions of the origins O and O' are indifferent, and we can translate the coordinate system x, y, and z from the point O to the point O' without changing its orientation. Then the relative orientation of the 2 coordinate system is determined as follows. First, we rotate the coordinate system counterclockwise about its z-axis by the angle psi. Then we rotate the coordinate system counterclockwise about its y-axis by the angle theta. In the last step, we rotate the coordinate system counterclockwise about its z'-axis by the angle phi such that the axes y and z are brought into the y' and z' axes. As a result, the Cartesian coordinates x null, y null, and z null of the origin O' of the coordinate system attached to the body, and the Euler angles theta, psi, and phi describing the directions of the coordinate axes specify the instantaneous position of a rigid body. After discussing how to specify the position of a rigid body, we will study the description of the change in its position, that is its motion in space. A rigid body can perform different kinds of motion, and one kind of its motion is called translation. During translation of a rigid body, all the points of a body simultaneously move along congruous curves parallel with each other. If the translation is performed along a straight line, then these curves are also straight line segments. As a result, every point of a rigid body has the same velocity at a given instant of time and the orientation of the body does not change during its motion. In such a situation, we only need one arbitrary point of the body to describe the instantaneous position of the body. Another important type of motion of a rigid body is the rotation about an axis. When a rigid body rotates, its points lying on the rotation axis remain at rest, whereas the rest of its points move along arcs lying planes perpendicular to the axis. In this case, we need not only an arbitrary point of the rigid body but also the orientation of a coordinate system attached to the body to describe its instantaneous position. These figures illustrate the difference between translation and rotation. The circles represent the trajectories of the points A and B of a rigid body during its motion. In the case of translation along a circular path depicted in the left-hand side, both the circles have the same radius but their centers are different. A well-known example for such a translation is the motion of the cabins of a Ferris wheel. The right-hand side figure shows either a rotation of a rigid body, where the rotation axis does not pass through the body, or a composition of one translation and a rotation with a rotation axis passing through the body. A simple example for this type of motion is a model railway traveling on a continuous circular loop, or the Moon orbiting the Earth, since the Moon keeps the same face to us. Now we can assume that the general motion of a rigid body is a composition of a series of infinitesimal translations and rotations of the body. We will illustrate this statement with a simple example. Let the 3 points specifying the position of a rigid body be the 3 corner points A1, B1 and C1 of an equilateral triangle at the instant of time t1, and let this triangle have another position in the with the corners at the points A2, B2 and C2 at the instant of time t2. Here the letter D denotes the length of the sides of the equilateral triangle. We can translate the triangle from its original position to the new one along the vector pointing from the point A1 to the point A2. As a result, the point A1 is translated to the point A2, the point B1 is translated to the point B'1, and the point C1 is translated to the point C'1. The points B'1, C'1, B2, and C2 lie on the sphere of the radius d with the center at the point A2. Now we draw a line passing through the point A2 such that a rotation about the axis represented by the line brings the points B'1 and C'1 into the points B2 and C2. The angle and the direction of the rotation axis can be determined by applying geometric considerations. The figure in the right-hand side shows the triangle A2B2C2 at the instant of time t2, and the translated triangle A2B'1C'1. We can represent the two sides with the corner A2 of the later triangle by the vectors pointing from the corner A2 to the corners B'1 and C'1. These vectors span the plane P' of the triangle and their cross product is perpendicular to the plane, that is, it gives the normal vector of the plane P'. Similarly, the two sides with the corner A2 of the triangle A2B2C2 are represented by the vectors pointing from the corner A2 to the corners B2 and C2. These vectors also span the plane P of the triangle and their cross product is perpendicular to the plane, forming the normal vector of the plane P. If we map the triangle A2B'1C' onto the triangle A2B2C2 by rotating it about an axis passing through their common corner A2, then the rotation axis lies on the angle bisector of the rotation angle measured between the planes P and P' of the triangles. As a result, the rotation axis is the intersection of the two planes passing through the point A2, and the axis is perpendicular to the normal vectors of the planes P and P'. This means that the rotation axis is parallel to the cross product of the normal vectors, and the angle phi between the two planes of the triangles gives the rotation angle. Both the direction of the rotation axis and the rotation angle can be determined from the coordinates of the corners of the triangles. If we calculate the cross product of the vectors pointing from the corner A2 to the corners B'1 and C'1, then its magnitude can be written as the product of the magnitudes of the vectors times the sine of pi over 3, the angle between the sides of an equilateral triangle. Since the length of the sides of the triangle is given by d, the magnitude of the cross product is equal to d squared times the square root of 3 over 2. The magnitude of the cross product of the vectors pointing from the corner A2 to the corners B2 and C2 is also given by d squared times the square root of 3 over 2 because the triangles are congruous. This result helps us to determine the rotation angle if we calculate the dot product of the normal vectors of the planes P and P', which can be written as the product of the magnitudes of the two normals, times the cosine of the angle phi measured between them. By substituting the magnitudes of the two vectors into this equation, we obtain 3 over 4 times d to 4, times cosine phi. For given triangles the coordinates of the points A2, B'1, C'1, B2 and C2 are known. Then the cross product of the plane's normals can be computed from the coordinates of the points. Similarly, the left-hand side of the scalar product of the plane's normals is determined by these coordinates. Since the length d is fixed for the triangles, we can express the cosine of the rotation angle as a function of the coordinates. We can also translate the triangle A1B1C1 along the vector pointing from the point B1 to the point B2 to the position described by the triangle A'1B2C'1. Then we need to rotate the later triangle about an axis passing through the point B2 to bring it to the position of the triangle A2B2C2. Although the translation vectors are different and the rotation axis passes through different corners of the triangles in the two cases, both the axes have the same directions and both the rotation angles are the same. It follows from the fact that the plane P' of the triangle A'1B2C'1 is parallel with the plane P', and the intersection of the planes P and P' is parallel to the intersection of the planes P and P'. As a result, the rotation axes of the two cases have the same direction. Similarly, the rotation angles are also the same because the angle measured between the planes P and P' is also equal to the angle between the planes P and P'. It can be shown that the result illustrated here holds for an arbitrary solid body. That is, the displacement of a rigid body is equivalent to the combination of its translation and a rotation about an axis. The translation from a given starting point P1 to the point P'1 during the time interval delta t is described by the vector pointing from P1 to P with the length delta s. If we consider rigid body motion during an infinitesimal interval of time, then the infinitesimal motion of the body consists of an infinitesimal translation given by the differential of the displacement and an infinitesimal rotation given by the differential of the rotation angle. For an infinitesimal translation, we can define the velocity of the translation by the ratio of the distance delta s of the translation to the time interval delta t, as delta t tends to 0. In other words, the magnitude of the translation velocity or the speed of the translation is equal to the derivative of the arc length s measured along the translation with respect to the time t. The rotation of the point P'1 about a given axis during the time interval delta t brings the point to the endpoint P2, where the rotation angle delta phi is measured between the sections OP'1 and OP2. For an infinitesimal rotation about an instantaneous axis of rotation, we can define the angular velocity omega of the rotation by the ratio of the angle delta phi of the rotation to the time interval delta t, as delta t tends to 0. That is, the angular velocity of the rotation is equal to the derivative of the rotation angle phi with respect to the time t. In the example shown as an illustration of the decomposition of the rigid motion, we saw that the translation of the rigid body, therefore the velocity of its translation depends on the choice of the starting point used for the translation, but the direction of the rotation axis and the angle of rotation do not. The angular velocity of the rotation is therefore independent of this choice. As a result, we can find a starting point for the translation such that the direction of the translation is the same as the one of the rotation axis. In other words, the displacement of the body can be described with a helical motion. This statement can also be illustrated with the same example, where the equiliteral triangle A1B1C1 is displaced into the position described by the triangle A2B2C2. We have a unique direction of the axis about which we can rotate the triangle while it is translated along the axis due to its independence of the position of the initial translation point. This choice results in a helical motion, where the points of the first triangle can be brought along helical trajectories into the corresponding points of the second one. In the case of the corners A1 and A2 of the two triangles, we can find a helix passing through the 2 points, where the axis of the helix is the axis of rotation. Then the trajectory of the moving point A1 during the interval of time delta t is the section of the helix connecting the points A1 and A2. Similarly, another helical path can be drawn with the same axis passing through the corners B1 and B2, and its section connecting the 2 points represents the trajectory of the moving point B1 during the same interval of time. A third helix passing through the corners C1 and C2 gives the path of the point C1 covered by its motion during the time interval delta t. If delta t tends to 0, we can talk about the motion during an infinitesimal interval of time, and we conclude that the most general motion of a rigid body can be interpreted as a series of infinitesimal helical motions. After having defined the angular velocity of a rotating rigid body, we show how to interpret this kinematic quantity as a vector. Let us consider a rigid body rotating about a fixed axis passing through the points O and A with the angular velocity omega. An arbitrary point P of the rotating body described by the position vector R has a circular trajectory around the point A, and we can apply the formula obtained for circular motion stating that the magnitude of the velocity v of the point P is given by its distance ρ from the axis, times the angular velocity omega. If the angle between the rotation axis and the position vector R is denoted by theta, then the distance ρ can be written as the length of the vector R times sine theta, and the speed of the point P is equal to omega times R, times sine theta. The right-hand side of this equation reminds us the magnitude of the cross product of two vectors given by the product of their magnitudes times the sine of the angle between them. As a result, we can consider the angular velocity omega as a vector lying on the rotation axis with its tail at the point O and with an orientation determined by the right-hand rule. By applying the notations of the figure, we can write this vector as omega times a unit vector pointing upward, where the unit vector is expressed as the vector pointing from the point O to the point A divided by its length. If we held the axis with our right hand and rotated the fingers in the direction of motion of the rotating body, then our thumb would point the direction of the angular velocity. In this figure, the angular velocity omega points upward along the axis of rotation, whereas the instantaneous velocity v of the point P is the tangent to the circular path of the point, and perpendicular to the plane spanned by the angular velocity and the position vector r of the rotating point. Then the instantaneous velocity v of the point P of a rotating rigid body with the angular velocity omega is given by the cross product of the angular velocity vector omega and the instantaneous position vector r pointing from the point O to the point P. For infinitesimal rotations, it is justified to consider the angular velocity as a vector, since the parallelogram rule holds for any two rotations with rotation axes intersecting each other at a given point. If the instantaneous angular velocity omega one of the body points in the direction of the OA axis, the infinitesimal displacement ds1 of the point P during an infinitesimal time interval dt is given by the product of the instantaneous velocity v1 of the point P and the time interval dt. Then the displacement is equal to the cross product of the angular velocity omega 1 and the position vector r of the point P, times dt. Similarly, for the angular velocity omega 2 pointing in the direction of the OB axis, the infinitesimal displacement ds2 of the point P is equal to the instantaneous velocity v2 times the time interval dt, that is the cross product of the angular velocity omega 2 and the position vector r, times dt. For both of the rotations, the infinitesimal displacements of the point P along its circular path are equal to the infinitesimal displacement vectors in the first order. If we rotate the point P with the angular velocities omega 1 and omega 2 either simultaneously or successively, then the net displacement ds of the point P is given by the vector sum of the displacements ds1 and ds2. However, we obtain the same net displacement if we compute the vector sum omega of the angular velocities omega 1 and omega 2, and construct the displacement ds as the cross product of the vector omega and the position vector r of the point P, times dt. This statement follows from the comparison of the similar triangles seen in the vector sums of the angular velocities and the displacement vectors. We can go even further in the interpretation of a rotation as a vector. Since the angular velocity omega of an infinitesimal rotation is a vector, its product with the infinitesimal interval of time dt is also a vector, and it can be interpreted as the infinitesimal rotation vector d phi. The infinitesimal change dr in the position vector r of a given point P of the rotating body is always perpendicular to both the axis of rotation, that is the vector d phi, and the instantaneous position vector r. As a result, the infinitesimal displacement of the point P can be written as the cross product of the infinitesimal rotation vector d phi and the position vector r. However, small but finite rotations cannot be considered as vectors because the parallelogram rule does not hold for them and the finite rotations are not commutative. For example, let us consider a cuboid in a Cartesian coordinate system. We can rotate the cuboid first about the x-axis by 90 degrees, and then about the y-axis by 90 degrees. But we can change the order of rotations and rotate it first about the y-axis by 90 degrees, and then about the x-axis by 90 degrees. As a result, the cuboid has different positions and orientations after the composition of rotations in the two cases. If any finite rotation can be constructed by the sum of the infinitesimal rotations, how can finite rotations be commutative and the infinitesimal ones not? In fact, infinitesimal rotations commute only in the first order, as we approximated the infinitesimal displacements along the circular path of the rotation with displacement vectors in the first order. If we study the general motion of a rigid body, we can choose the reference point O attached to the frame of reference and another reference point O' attached to the moving body given by the instantaneous translation vector r0. Then any point P of the body can be described by the position vector r pointing from the point O to the point P, and the relative position vector r minus r0 pointing from the point O' to the point P. We already saw that the instantaneous velocity v of an arbitrary point P of a rigid body performing a general motion can be combined from the translation and the rotation about the axis passing through the point O'. Here the translation velocity v0 of the body is given by the derivative of the translation vector r0 with respect to the time t. The origin O' was chosen such that the instantaneous axis of rotation with the angular velocity omega passes through it. Then the velocity v of the point P is given by its translation velocity v0, plus the cross product of the angular velocity omega of the rotation and the relative position vector r minus r0. Now we present the special cases of rigid body motion in terms of kinematics based on the degrees of freedom of the moving body. In the beginning of the study on the kinematics of rigid bodies, we introduced the degrees of freedom of their motion as the number of independent variables that determine the instantaneous position of a rigid body in space. Based on this concept, we can divide rigid motion into two general groups. The first group describes the free motion of rigid bodies, which is their most general motion since free motion has the maximum degrees of freedom. As already seen, the degrees of freedom f describing the free motion of a rigid body is equal to 6, where 3 data determines the coordinates of an arbitrary point of the body associated with the translational motion and called translational degrees of freedom, and 3 angles determine the orientation of the body known as rotational degrees of freedom. The second group describes the constrained motion of rigid bodies. In this case we talk about special motions where the degrees of freedom are less than the maximum, that is f is less than 6. For rigid motion we can write the degrees of freedom f as the difference between the maximum, that is 6, and the number n of the constraints imposed on the motion. We already studied constrained motion in the case of a point mass, and this concept can also be applied for a rigid body, where constraints are imposed either on its motion or its position, or on both, limiting its motion and position. For the rigid motion described in a coordinate system, constraints are given by the equations of geometric elements representing some restriction in the motion of the body. Such geometric elements can be some set of fixed points of the rigid body, curves, or surfaces. For example, a set of fixed points can determine one or more fixed points of a body or even a rotation axis passing through the body, along which the points of the body do not change their position during its rotation. Similarly, if a ball is attached to a string and whirled in a circle by hand, then the motion of the ball is constrained such that the curve describing its trajectory in space is a circle. In the third example, the ball rolls on a curved surface of a ramp preventing it from free fall, and the surface represents a constraint on the motion of the ball. These examples demonstrate that the points of the rigid bodies have no instantaneous displacements perpendicular to the curve or the surface representing the constraint. The ball whirled in a circle has no motion in the radial direction of its circular path, and the ball rolling on the curved surface had no instantaneous displacement in the direction of the surface normal. We can talk about several types of the constrained motion of rigid bodies depending on the number of constraints imposed on the motion. The first type of constrained motion is the motion of a rigid body on a surface, for example the motion of a wheel or a ball across a floor or a table. Here the degrees of freedom f of the moving body is equal to 5 since the translation perpendicular to the surface is forbidden during the motion. Such a motion has different cases. If we mark the instantaneous contact points of a moving ball across a table on both the ball and the surface of the table at given intervals of time, then the curve connected with the points P1, P2, P3 etc. on the surface, and the curve connected with the points P1', P2', P3' etc. on the ball can describe the motion of the center of the ball. If the arc lengths delta s measured between the corresponding adjacent points of the two curves are equal, that is the length of the section P1 P2 is equal to the length of the arc P1', P2', the length of the section P2 P3 is equal to the length of the arc P2', P3', and so on, then the ball rolls on the planar surface like a billiard ball moving across the table when it is hit with a cue stick. Otherwise we talk about rolling sliding motion instead of pure rolling, which can be also demonstrated with a billiard ball hit below its center. The ball performs pure sliding if the locations of the points P1, P2, P3 etc. on the ball remain the same as in the case of a bumper ball, which can also slide across ice. If the position of the contact point remains the same on both the rigid body and the surface, and the body rotates about an axis which is perpendicular to the surface and passes through the contact point, then the motion is called spinning or drilling. As an example, we can consider a marble spinning on a surface or a more illustrative one of a basketball spinning on one finger. Another type of constrained motion is called spherical motion, where the rigid body is fixed at a point O such that it can rotate about this point while any other point P of the body can move over a spherical surface with the center O. This type of motion can be considered as a series of infinitesimal rotations about instantaneous axes of rotation passing through the point O. As a result, the motion has only 3 rotational degrees of freedom given by either the Euler angles, or more generally by 2 angles describing the direction of the instantaneous rotation axis and a third angle measuring the rotation of the body about this axis. A typical example of spherical motion is the swinging of a spherical pendulum, where the deepest points of the tracks drawn in the sand by the tip of moving bob have a constant distance from the suspension point O of the pendulum, that is, they are running over a sphere with the center O. Another well-known example is the spinning top with its tip constrained to a cup. While its tip remains at the bottom of the cup, the top spinning rapidly about its own axis can also precess around a vertical axis through its point of support. The third type of the constrained motion of a rigid body is its planar motion, where the trajectories of the points of the body are parallel with a fixed plane in the space. For example, in the case of a box sliding across the xy plane over an arbitrary path, the position of the body is determined by the positions of 2 points A and B of the body lying in the xy plane. As a result, the degrees of freedom of the moving box is equal to 3, and this data can be, for example, the x and y coordinates of either the point A or the point B, and the angle phi between the segment AB and the x-axis. This happens when we slide or rotate furniture on the floor. The planar translation of an object, for example a motion of a wheel across the floor in a given direction, is a special case of planar motion since the degrees of freedom f is reduced to 2. The condition of rolling for a wheel can be illustrated in the figure of the rolling ball, and it states that the delta s arc length of its trajectory must be equal to the radius r of the wheel, times the angle delta phi measuring the rotation about its axis. Here the instantaneous axis of rotation is perpendicular to the plane of the wheel, and the axis of the wheel is translated in the direction parallel with the plane of the wheel. The last type of constrained motion is where the degrees of freedom of the moving rigid body is equal to 1. We can talk about two cases of this type of motion. The first case is the linear translation of a body, where one coordinate can measure the displacement of the body along the translation vector. Here the trajectory connecting the initial and final positions of an arbitrary point A of the body is a straight segment across the xy plane, and the distance between the two positions is the single degree of freedom determining the motion. A typical example for linear translation of the motion of the printer head during printing. The second case is when 2 points of a rigid body are fixed and the body can only rotate about the fixed axis passing through the 2 points. A well-known example for such motion is the operation of ball bearings, where one of the races is fixed while the other one is allowed to rotate by the separated balls between the races. Here the only degree of freedom of the motion is the rotation angle of the moving race. Helical motion has also only one degree of freedom, as the example of a nut turning on a bolt shows. Although this motion is the composition of a translation and rotation, the rotation angle uniquely determines the position of the nut along the axis of the bolt. Vice versa, the displacement of the nut along the axis of the bolt also determines the rotation angle of the turning nut.